Hello friends, today we are having a look over electric field and charges, very first chapter in physics in class 12th, and Sam is having trouble, and if you want to know who is Sam, just click onto the previous video and check it out. Now let's just help Sam. Now he want to know what is electric field and electric charges. Now let me ask you some questions first, that have you ever wondered how Xerox or photocopy is done? And why pen attract pieces of paper when rubbed with a cloth? Why laptop screen collects dust so easily? The answer of all above questions can be answered if we study the branch of science that is called electrostatics. So let's just check it out. What is electrostatics? Electrostatic is a branch of the science which deals with how electric charges behave at rest in a free space or a medium. First, let's see what is an electric charge, because after reading the title you must be wondering what is in charge. Charge is a physical quantity of a matter due to which a matter experiences a force when placed in electromagnetic field. So charges can be of two types, like positive and negative, and this sign convention were proposed by Benjamin Franklin, and you can see him on $1 bill. SI unit of a charge is Coulomb. And if we talk about the subatomic particles, that is electrons, protons and neutrons, electrons are negatively charged, protons are positively charged, and neutrons are neutral. They have no charge on them. These electric charges have some properties. Charge is quantized. It follows law of conservation of charge and law of additivity. Quantized means all the charge in the universe is in integral multiple of the charge on one electron, that is mathematically Q is equals to Ne. And you might be wondering how much charge an electron holds, that is 1.6 into 10 raised to a minus 19 coulombs. Benjamin Franklin proposed that like charges repel each other and unlike charges attract each other. So when we put two negative charges side by side, they will repel each other, but if we will put two unlike charges, that is one positive and one negative charge, they will attract each other. Now let's talk about principle of superposition. It states that the net electric force on a charge is equivalent to the algebraic sum of the electric forces due to all other charges around that charge. And if we're talking about electric force, we should have a look on Coulomb's law. Coulomb proposed when we have two charges in a space separated by a distance r, the electric force will be directly proportional to the product of the charges and inversely proportional to the square of distance between them. And mathematically, F is equals to 1 by 4 pi epsilon naught Q1 Q2 by r square. According to Coulomb's law, force is directly proportional to the product of magnitude of charges, and force is inversely proportional to the square of distance between them. Combining both above equation, we get force is equals to K Q1 Q2 by r square newtons, where K is an electrostatic force constant. K is equals to 1 by 4 pi epsilon naught, and value of K depends upon the nature of the medium. In CG system, the value of K is equals to 1 for a free space, whereas in SI system, value of K is 9 into 10 raised to 9 Newton meter square per Coulomb square, where epsilon naught is the absolute electrical permittivity in vacuum, that is free space. We will talk about epsilon naught in our next video of capacitance. Now value of epsilon naught is 8.85 into 10 raised to minus 12 Coulomb square per Newton meter square. Consider 2-point charges Q1 and Q2 such that R1, R2 are their position vectors. Hence, they will experience an electrostatic force on each other, that is F12 and F21. F21 is force on charge Q2 by Q1. Since force is a vector quantity, we have to tell the direction as well. Therefore, R12 is the direction in which it is acting. That is, R12 is a unit vector telling the direction of the force. Similarly, F12 is a force on charge Q1 due to Q2. Important thing to notice is that R21 is equals to negative of R12. If anyone of you don't know about vectors and you want me to explain that, just comment down below. We'll explain that via audio note on Snapchat, or simply DM me on Insta, or just simply comment. I will make a video. Now it's all mathematics. We will find the value of F12 in terms of F21. And by substituting R21 is equals to negative R12 and simplification, we will get F12 is negative F21. And this shows that the force exerted by charges on each other are equal in magnitude and opposite in direction. And this is expression for the vector form of Coulomb's law. Now let's jump into electric field. Actually, electric field gives a broader picture of two charges interacting each other, or how a charge interact in a free space in its surrounding. Electric field is defined as a region or a space around a charge in which an electrostatic force can be felt by another charge. Anything outside that electric field, the outer boundary electric field, is infinity for that charge. It means at infinity from that charge, no force can be felt by a test charge if we keep a test charge outside the electric field. Now, what about its strength? If we talk about electric field, now what about its strength at a point? Let's discuss that. And that strength is defined by electric field intensity. Electric field intensity is defined as a field strength at a particular point experienced by a unit positive charge at that point. That is measure of electrostatic force experienced by a unit positive charge at that point. Let's see how a electric field intensity looks like for a point charge. We have assumed a charge positive q and a test charge q naught separated by a distance r. Now Coulombic force between them will be F k q naught by r square. That is force exerted by q on q naught. By definition, electric field intensity is defined as electric force experienced by a unit positive test charge. Mathematically, E is equals to F by q naught. After doing basic evaluation, we'll get E is equals to Q by 4 pi epsilon naught r square. This is expression of electric field intensity at r due to a charge positive Q. Also, the direction of electric field intensity will be along the line joining the point O and P. Now let's talk about graphical representation of electric field. And tangent at any point on electric field lines gives the direction of the field line at that point. For example, think of a positive charge in a free space. The direction of field lines from a positive charge will be radially outwards. Now we should know some basic properties of electric field lines. And the first one is, for a positive charge, direction of electric field line is radially outwards, and for a negative charge, it's radially inwards. Second, tangent on field lines gives the direction of electric field at that point. Third, no field line can intersect each other. An intersection point on field lines will give two possible tangents at that point, and that means two different directions of field lines at the same point, and that is impossible. Fourth, electric field line must origin on positive charge and they must end on negative charge. Fifth, crowded field line means stronger electric field and vice versa. Now let's think about two equal and opposite charges separated by a very small distance. Yes, you are right. We are talking about an electric dipole. Let's see what it is. An electric dipole, as mentioned before, is a set of two equal and opposite charges separated by a very small distance and defined as electric dipole. Also, we will have a look on dipole moment. It is denoted by a p vector, and mathematically p is equals to q into 2d. Dipole moment is defined as a product of magnitude of one of the charges and the distance between them, that is p is equals to q into 2d. It is in a vector quantity and SI unit of p is Coulomb meter. Now we will head towards the important expression of electric field intensity due to an dipole on an axial line and equatorial line. Let's find out the electric field intensity due to dipole at an axial line. First of all, we should know what is an axial line and equatorial line. Let's define that first. A line passing through the centers of the positive and negative charge is defined as axial line, whereas a line passing through the center of the dipole and perpendicular to the axial line is called equatorial line. Now consider a dipole AB, negative Q charge on A and positive Q charge on B. O is a midpoint, and that is AO is equals to OB equals to D. We need to find electric field intensity at point P at r distance from the center of the dipole O. We have assumed a test charge lying on that point P, and from a general formula we studied a few minutes back. Electric field intensity for a point charge is 1 by 4 pi epsilon naught q by L, where L is the separation between the test charge and the source charge. Firstly, we will find our electric field intensity on a point P due to the charge, that is positive charge, placed at B. That is, we will call this field intensity E1. E1 is equals to 1 by 4 pi epsilon naught q by R minus D whole square. We just plug in the values of q and R in a general formula and got this expression. And the direction of the field line will be along the direction of dp. Similarly, electric field intensity at a point P due to negative charge placed at point A, that is E2, will be 1 by 4 pi epsilon naught q by R plus D whole square, and the direction will be along PA. It's clear that E1, E2 acting in two different directions, and the net electric field intensity will be the algebraic sum of the both. That is, E net is equals to E1 plus negative of E2. After evaluation, we will find this expression, and we know that for a dipole D is very small than R. That is, point P is very far away from the dipole. Therefore, D square can be neglected, and electric field intensity at point P will be 2q2d by 4 pi epsilon naught r cube along direction dp. Since P is equals to q into 2d, just plug in the values and we'll get electric field intensity will be, and we can clearly see that electric field due to dipole acts in the direction of dipole moment. We have just derived E axial, now we have to find out E equatorial. Now, electric field intensity due to an electric dipole at a point on equatorial line is actually E equatorial. Just like before, we'll find out the field intensity at a point P due to negative q charge and positive q charge separately, that is E1 and E2. Hence, E1 is equals to q by 4 pi epsilon naught dp square along dp, and E2 will be q by 4 pi epsilon naught ap square along pa. And we know that ap, and from the diagram we can see that ap is equals to dp and equals to under root r square plus d square by Pythagoras theorem. Now, after evaluation, we can see for the net electric field intensity, we'll have a vector sum of both E1 and E2. And for the ease of our calculation, we will resolve the E1 and E2 in horizontal and vertical components. The net vertical component will be 0 since mod of E1 is equals to mod of E2. Therefore, net electric field intensity at point P will be the algebraic sum of the horizontal component of E1 and E2, and which gives net electric field intensity, that is E net, is equals to twice of E1 cos theta. And after plugging the values of E1 and cos theta from triangle AOP, we'll get this expression. And again, we know that D square can be neglected as D is very small than R. Therefore, electric field intensity on a equatorial point will be E by 4 pi epsilon naught r cube along direction ER. Now, if you feel like that this lecture was helpful and you people want more videos, just comment down below what are your problem areas. Make sure to subscribe, comment, share this channel. Peace.